Hey, what's up, chemistry people? It's Mr. Boylan, and today we're going to talk about excess and limiting reactants by making some sandwiches. It's a pretty straightforward concept. If you take a look, you need an equation. In this case, our equation is going to be 2 slices of bread plus 1 slice of cheese is going to make 1 cheese sandwich. I'm going to give us just a couple of each of our reactants to start so we can begin to understand this idea of excess and limiting reactants. Again, it's really important with any stoichiometry problem that you take a look at the relationships that exist in your balanced chemical equation. And as we take a look at our reactants here, we have 2 slices of bread and 2 slices of cheese to start with. However, we can't make 2 cheese sandwiches. We can only make 1. We are limited in the number of sandwiches we can make based on the number of slices of bread. So because we have 2 slices of bread, we can only make 1 cheese sandwich. And that can be kind of confusing at times, especially if you were to look at the cheese. You might just think to yourself, oh, I have 2 slices of cheese, I can make 2 sandwiches. And then, no. I mean, how many times does this happen when you go to the fridge and you pull out some cheese, you're like, yes, grilled cheese sandwiches, and then you go to the cupboard and you're like, oh man, can't really make as many grilled cheese sandwiches as I wanted. Bottom line here is that a limiting reactant is the one that's going to run out first. Your excess reactant is going to be one that remains unreacted after the reaction has used up all of that limiting reactant. So we can take a look at some different numbers here, sort of play with this idea of excess and limiting reactant. Let's say I started out with 4 slices of bread and 3 slices of cheese. Again, as we look at our balanced chemical equation, for every 2 slices of bread, I need 1 slice of cheese to make a cheese sandwich here. And so these 4 slices of bread will help me make 2 sandwiches. I will only use 2 of the 3 slices of cheese to make those 2 sandwiches, and I'll have 1 slice of cheese left over in excess. Now, it doesn't always have to be the cheese that limits your reaction. If I had, for example, I don't know, 8 slices of bread and 3 slices of cheese, we've got enough bread to make 4 sandwiches. However, we only have enough cheese to make 3 sandwiches. Again, that comes back to our relationship between the bread and sandwiches and our cheese and sandwiches. And so in this example, we'll only use 6 slices of bread to make our 3 sandwiches. 2 slices of bread will be left over, unreacted, in excess. We will use up all 3 of the slices of cheese. They're going to be our limiting reactant in this example. All right, you can also apply this to real chemical equations, although the cheese sandwich equations are way more fun. In fact, you can practice the cheese equations at home and then eat them when you're done. But same thing applies here. We just have a new chemical equation here. We're making water instead of cheese sandwiches. The relationship between hydrogen and oxygen here is 2 to 1. And for every 2 hydrogen molecules that react with 1 molecule of oxygen, we'll make 2 molecules of water. And so I'm going to start again with just 2 hydrogen and 2 oxygen. And as you see here, before the reaction, we have 2 of each of them. However, after the reaction, we have 2 water molecules and 1 leftover oxygen molecule that is unreacted. And again, that just comes down to the relationship that we see in the balanced chemical equation. For every 2 molecules of hydrogen, we'll make 2 molecules of water. For every 1 molecule of oxygen, we'll make 2 molecules of water. Now I could go on and do all sorts of combinations. In this example, I start with 5 molecules of hydrogen and 2 molecules of oxygen, and I make 4 molecules of water, and 1 molecule of hydrogen remains unreacted. You can mess around with this on your own. This PhET simulation is a great one to practice with and better understand the concept of limiting reactants. All right, chemistry people, what the heck are we going to do today? So we're going to continue with stoichiometry today. So I can relate quantities, measured mass of substances, volumes of solutions, or volumes and pressures of gases to identify stoichiometric relationships for a reaction, including situations involving limiting reactants and situations in which the reaction has not gone to completion and apply this knowledge to the lab setting, including gravimetric analysis and titrations. So basically, stoichiometry on steroids. All right, so as we look to break that down just a little bit here, again, we're still just doing some stoichiometry, but now we have to watch out for those cases in which one of the reactants is going to limit how much product we can make. And then we're also going to do some stoichiometry that involve just some laboratory processes, including gravimetric analysis and titrations. And again, these are just lab procedures that we're going to work on in class, and you're going to focus on the stoichiometry as you work through those procedures. Boom. So, as we take a look at understanding what's going on with stoichiometry using excess and limiting reactants, first thing is we're going to do some quick definitions here. A limiting reactant or limiting reagent, those two you'll hear interchangeably, is a reactant that will be completely used up during the chemical reaction, and it's going to determine all other amounts. So really importantly here, when you're given a stoichiometry problem and you're given the amounts of two reactants, before you start, you've got to figure out which one's going to limit the reaction. Second thing here then is what the heck is an excess reactant? Well, if the limiting reactant is the one that's going to run out first, the excess reactant is going to be the one that will not be completely used up during the chemical reaction. There'll be some left over at the end of reaction that is in its original form. Boop, 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 doo-doo. And then lastly here, percent yield is simply a method to calculate the effectiveness of a chemical reaction. You're going to be looking at how much you actually make in the lab when you run the reaction versus how much you theoretically should get if you were just doing pen to paper and doing the stoichiometry to figure out how much you should have gotten. Your formula for percent yield is a short but sweet one. You take your actual yield you got in the lab, divide it by theoretical yield, and then multiply that by 100. And then lastly here, just a couple of quick definitions about some of those lab processes that we talked about in our content objective. Gravimetric analysis uses the formation of a solid and a balanced chemical equation to allow for the quantitative analysis of a dissolved analyte. So as you take a look at this image to try and better understand what's going on with gravimetric analysis, if you've got some initial sample that's soluble in solution, and then you mix it with some other soluble solution that will cause some part of that initial analyte to precipitate out of solution, you can then analyze that precipitate and do a lot of really fun stoichiometry with it. And then the other technique we're going to talk about here and work with in class quite a bit is titrations. And again, a titration is just a technique that uses a titrant, something with a known concentration that you add to an analyte up to the equivalence point. So here's a quick image of a titration setup where you've got your burette that contains your titrant, the thing that has the known concentration, and your analyte here of unknown concentration in the flask beneath it. Then you'll add the titrant to your solution here in the flask until you reach the equivalence point. And there are a couple of things to keep in mind here about titrations. One, the equivalence point is the point at which the analyte is exactly and totally consumed by the titrant. And generally, it should be accompanied by some observable change, oftentimes a change in color, so we can visually see when we've reached that equivalence point. The point at which that color change is observed is known as the end point. So again, the equivalence point is where you've got the stoichiometric relationship that you see in the balanced chemical equation. The end point is where we see that color change. Now, if you've set your titration up correctly, the end point should occur at approximately the same place as your equivalence point.